So I found this introduction very nice in the paper by Nikolai Baldin and Volodya. Well, let's see what happens if you just take kind of, because it's Gaussian model, you have the negative log likelihood, that is kind of a norm squared divided by 2 delta squared, because delta is the noise level here. And the point is, if T is an infinite dimensional operator, then this minimization problem is not possible, not feasible. There's no minimizer in general, unless the data are in the range of the operator. And then it's unstable. So that's why it does not make sense to consider this minimization problem like a least squares problem, regression, finite dimensional regression. So that's why what you do is you add a penalty, right? That's called what is called quasi-likelihood. That's a likelihood from before, and you add a penalty, and the penalty is that you enforce the solution to that problem to be smooth. That's kind of a requirement to enforce the solution to be smooth, and omega 0 is a trace has a finite trace. So this is kind of the smoothing map which says that this is finite if x is in the domain of this operator. Otherwise, it's infinite, and then you will not have a minimizer. So that enforces x to be smooth, and then this problem is well posed, so we can receive the minimizer by some means. I don't know, it's explicit here, you can see what it is. That's an explicit representation of the minimizer, depending on this parameter alpha, and everything will be about alpha. And like in regularization theory, everything is about alpha. So how to choose alpha? That's the main problem. And the paper by Nikolai and Volodya says, well, we are true Bayesian, so alpha is a hyperparameter, we put a hyperprior on the alpha, and then we look what it would be the posterior alpha. What I propose here is to choose alpha deterministically based on the data, and that will be Oracle type, so it cannot be beaten even by the most sophisticated Bayesian choice. Okay, so that's the setup. Well, so far we have just penalized likelihood, and this transforms in a very easy computation. So e to the minus quasi-likelihood is just the product of these two quantities. As you can see, this is the sample distribution, that means the distribution of the data given x. It's Gaussian under our assumption, and this is a prior distribution. You may view this as a prior distribution. So this is a prior, which corresponds to this choice. So you may view this problem of the minimization problem also as a Bayesian problem and see, well, what will be the posterior distribution. Let's see what is the posterior here. The posterior is the following. You have the notation is following. So given alpha and given data. So you have specified alpha here, and you have specified the data. Given the data. The posterior will be also Gaussian. If omega sub 0 has a finite trace, it will be type Gaussian. It means a real, Radon Gaussian measure in Hilbert space. So a proper posterior. And x alpha hat, that means the minimizer from the previous slide. Here, this minimizer will be the posterior mean, which is very specific for the Gaussian model. And everything can be made rigorous because, as you can see here, typically in Hilbert space, the Gaussian white noise data y delta do not belong to the Hilbert space. So they are not a member of the Hilbert space, so that's why formally this is just formal chalk, but it's not meaningful. But whereas you can, under the assumption here, you can construct this x alpha hat, because because T star is kind of smooth. Here's C0 somewhere, omega 0. So here you can see that this pushes everything as it should be into Hilbert space. So the question is, well, given alpha and given data y delta, does this distribution concentrate around the true means the data generating x star? So because the data will generate it by some x, otherwise I don't have data. So the question is, do they concentrate around x star as delta, the noise limit tends to 0? It's not written here, but that's the meaning. And the question is, if it concentrates, so what is the contraction rate? So at which rate does it contract to the true solution? So the guess will be, okay, it will concentrate. And the question is, with what speed will it concentrate around true solution, and what is the influence of the parameter alpha? So how do we need to choose alpha independent of the noise level? That's a major problem. As I said before, everything is about short-term alpha. Okay. What is the contraction rate? I found it very interesting because I didn't know about this notion, and actually I asked several people to tell me where does it come from. The first paper I could locate was Knappig et al. In the Annals a few years ago. They have a slightly different setup. But anyway, this is kind of the notion. What you do is, so X star is the data generating point. That means that was the point where it should concentrate around. And what you want is, well, if delta tends to 0, then we want to have an epsilon such that for this particular epsilon, if m tends to infinity, this should be tend to 0. And the point with this contraction is the following, because I have just one set of data, right? One X star. So the question is, the contraction will be point-wise. That means for each particular X star, I will have contraction rate. Whereas the second notion, that was the one you can find in all the papers, is uniform. So given a kind of smoothness class, you choose alpha depending on the smoothness class and get a contraction rate. But this is uniform on this class of smoothness class. But this is not very natural because actually what you have is X star, one specific element. And in a similar context, at least the second part is discussed there. Okay, and the analysis before, there were a few papers on this contraction rates, one by Knappig and co-authors, at least two by Knappig and co-authors. They considered the commutative case. So everything diagonalizes more or less. And then there's one paper which is very strange by Agapio, Larsson and Andrew Stewart from Warwick. And they consider the non-commuting case. And that raises technical difficulties. I have a solution to that problem also, but I will talk about the commutative case today. Because, just to tell you about the orego-type nature. Okay, so now we know what is a contraction rate. So the point is, choose epsilon depending on delta, and if delta tends to 0, epsilon will tend to 0, but whenever m tends to infinity, this will tend to 0. So that's kind of a very artificial, out of the mind notion. Actually, I asked Krillin, the student, to simulate contraction rates. So make a simulation, set up a MATLAB, and tell me, well, I have data and so on and so forth, what will be the contraction, the observed contraction rate? I could not find any way how to simulate the contraction rate. Very strange.
So you ask
yeah.
to make it more precise. So you fix X star,
yeah.
And then n tends to infinity. In your case,
m, yeah.
M, yes, but also.
No, there's no data here. N is 1 over delta squared.
Because I mean, is it asymptotic or it's for fixed data?
No, it's asymptotic. As delta tends to 0. No, here this is fixed. For fixed delta and fixed epsilon, this should tend to 0 when m tends to infinity.
But why it isn't rate? So what is the meaning of the word rate?
That is how to, you want to, there will be next slide. So the rate means that epsilon should be chosen as small as possible. And still, if m tends to infinity, it should tend to 0.
The rate is purely asymptotic notion.
Yeah, the rate means you want to choose epsilon as small as possible, depending on delta.
And delta will go small.
And delta will then tend to 0, and epsilon will tend to 0. This is the rate. Epsilon is a function of delta. And still there's third part of alpha. So alpha should be a function of delta, and then everything depends on delta, and delta tends to 0, and epsilon will also tend to 0. That's will be the rate. Whereas this concept is kind of fixed epsilon, m tends to infinity, it should be tend to 0.
But still, for this asymptotic fixed star is considered fixed.
Fixed, yeah. That's one X star.
Isn't that always the case? If epsilon is fixed and you send m to infinity, then this should go to 0?
Well, as you can see, the probability itself depends on alpha and delta. I will give the next slide. Here what you see is the following. You bound this probability. Here is the probability inside, and then you apply Markov's inequality and Chebyshev's inequality. There's two steps. And what you see is this is bounded. So the goal here is that for fixed u is now fixed. If epsilon square if this quotient here is bounded, then m tends to infinity and that tends to 0. So that is kind of the concept. So actually I don't care about too much, but this is the point. So if epsilon square should not be too small. If epsilon squared is too small, then it will not tend to 0. Epsilon is a function of delta, and delta tends to 0.
But, I mean, indeed, usual results are asymptotic but uniform on some functional classes.
Yeah.
And so, I mean, if you consider pointwise like nothing, I guess give it monosymptotic for one fixed data sample, then you can fix x. But if you fix x and your delta goes to 0, then it's a little bit weaker, the notion, the uniform contraction rate.
What does it mean, weaker?
It's not so strong. The result is not as informative as people usually get for uniform contraction rate. The technique is the same.
No. Here we have. Here the point is that we choose alpha based on the data, whereas otherwise you end on x, not knowing x star, of course. You have no idea about x star.
Yeah, but I just wonder about the notion of point-wise contraction rate. So this is a little bit strange. So usually contraction rate is defined on functional classes, and then you can.
No. That's in the minimax context. That's what you are. No, then the point is you have the possibility to choose your reconstruction as you like. And then, of course, at one particular point, I take as reconstruction the point itself. Everything is 0, I'm happy. But here, the estimator is given. The estimator is a posterior mean. And that's why it's not this flexibility as you might. So in the minimax context, it doesn't make sense. But here it makes sense. Because you have is a class of estimators, depending on alpha.
But we don't speak about estimator, we speak about the posterior distribution.
Yeah, this is given here. Posterior distribution is given here. That's the posterior distribution is Gaussian and so on and so forth.
Okay.
So what you see from this derivation here is the following: that we need to have epsilon at least of that size. That's one point, not too small. And the second one is, of course, you want to make this quantity as small as possible in order to have epsilon as small as possible. So the goal of this talk is kind of how to make this quantity as small as possible, depending on alpha. Not knowing x star, of course. That's the setup. And what you can see, this quantity is kind, if you plug in the estimator and so on and so forth, use typical calculus, it is a sum of the reconstruction error, that means the reconstruction error by using this estimator, given alpha, and the true solution. That's a classical estimation error, the mean squared error. And you have an additional term which comes from the posterior covariance. So this is the point, here it is, the posterior covariance. So the question is how to make this quantity small.
So which estimator is this?
That was on the first line, the Tironov type, the rich estimator. Maybe I can go back, what's this up? This one. That's Tironov type estimator. That's actually a very crucial point. It's a very crucial point because if you have Bayesian setup, the minimizer is always a Tironov solution, so a rich regression. So there's no flexibility. Bayesian analysis in the Gaussian context is always, what else can you do?
You can also assume a Laplace prior for the...
Oh no, I mean Gaussian context. Everything is Gaussian.
Okay, if everything is Gaussian, then yes.
Then you have Tironov, nothing else.
If the prior is also Gaussian, then yes. Yeah.
There's actually an interesting problem because there is a variety, a zoo of estimation procedures in the world. The question is, can you incorporate the zoo somehow in the Bayesian context? And that's a subject of a different talk. Maybe I give it in our seminar, but because that's also an interesting observation we made. Okay, so this is the point. We want to minimize this depending by choosing alpha properly, given delta of course, and not knowing the solution of course. So if you look for this quantity here, it is again, so the estimation error is always a Bayes covariance decomposition. Here it is. So that's the bias. And this is the variance of the sample distribution under this estimator, and this is a posterior covariance. It's just simple calculations, and then you have this exact representation of this quantity of interest. And what you see from this here, from this slide, is because this norm here inside is always less than 1. That means that this variance alpha delta is always smaller than the trace of C alpha delta. So there's one natural relation which you cannot beat. And the major, that's what I see here, and the major problem is, are these bounds of same order? And actually it was observed in the other studies that, yeah, that's always the case. But for what reason? The question is why this is always the case. So there's no good reason for it. Unless you make kind of assumptions. And what we figured out is, well, there's a good reason that these have same, not same order, but a common bound which is tight. This is kind of a slight nuance. So I cannot prove that there's the other way around, but they have a bound which is tight for both. So what are the assumptions which make sure that these quantities have similar size? That's the basic assumptions, and I tell you the common bounds. So the basic assumption is this very strange one, which says, well, suppose that B star B is now any operator. In our context it was the composition. Let me just chalk. See? So T was the operator governing the equation. That was our original operator. Omega sub 0 was the prior covariance, and B is T times omega sub 0 to the 1/2. That's the operator B, which naturally occurs in all these types of analysis. And what we require is that the singular numbers of this, and because assumptions to follow, if this trace with the Q is finite, then you see that this sum will be finite also, because that's the tail of the sum, right? And what you require is that the properly averaged tail behaves like as in the beginning, because this is just the initial part of the sequence, and that is tail. So that looks very strange, kind of. And what the good news is, well, if everything is polynomial, that's true. If everything is exponential, it's true. So of course there must be counterexamples, but in all the cases studied so far, this assumption is automatically fulfilled. This is good news, but still this is assumption. It cannot be true in general, I guess.
Do you need this assumption for a certain Q or
for some Q? Next assumption. Next assumption is, well, we relate the prior, that's a prior. The prior should be a function of T star T. So omega sub 0 is T star T to the power P. And then you see, if you can recalculate everything in terms of B star B, P, and Q will be P over P plus 1. So that will be finite because the trace of omega 0 is finite, and then you are at a good setup. So the point to make is, people of course are concerned, well, if I'm true Bayesian, I put everything into the prior, not knowing the equation. So the usual setup is the other way around. So you choose the prior, and then you will need to relate the prior to the operator. This is also done, but this requires interpolation theory. It's a different setup. I doubt to tell you about it because it's a different world. You are not used to it. But it's possible. But if possibility, we consider a commuting case, so the prior is a function of the operator governing the equation. Okay. Now comes the estimate. When I have a tight common bound for this conditional posterior covariance and the estimation covariance. And therefore we introduce the effective dimension function. That's a function of give the operator, because the trace of B star B is finite, that's kind of assumed, and then this will be a finite function of this type. As alpha tends to 0, it will tend to infinity. And then the goal of the effective dimension is to scan kind of the whole spectrum of the operator B star B, and now we get tight bounds, so that will be the estimation variance. That's of the type, the effective dimension, alpha to the minus 1 over P plus 1. Alpha was a parameter in which we've chosen for the prior, and delta is a noise level. So that's a tight bound. And the posterior covariance the trace of the posterior covariance is up to a constant same bound. So that's, and that type means I cannot prove that's lower bounded, but it means that the best which is known, so to speak. And in some cases, on classes, for uniform cases, if you have considered classes of smoothness, this is known to yield optimal rates for construction at least. So,
do we know what the constant?
This constant C sub q depends on this constant C. That's actually C sub q. And everything depends, of course, on this type of, there are many constants involved. So that's asymptotic, you don't like it, but still, it gives you some insight.
But what I just want to comment, I guess this variance, either variance or the C, one of this value is related to the risk, to the variance of the optimal linear estimator. Because if everything is Gaussian, and if everything Gaussian, you can consider class of linear estimator. And I think so. This this can be optimized, and there is a Pinsker constant which describes the risk of optimal linear.
Yeah, this is known exactly, but in general, what you get is a bound of this type, and this is you can compute this decay of this function, and then you see that's more or less the same rate. So in summative type cases, it gives the same rate. So that's quite a good bound. And it's kind of universal, not depending on the type of estimator. Here, in our case, we have a Tikhonov type estimator, so everything is specific, but this bound is valid for every estimator, linear. Okay, so these are the type bounds, and what you then get is, well, as you can see, still everything depends on delta and alpha. So we want to choose alpha. And the point is, this is just a bound, if you look back, what we see here is, we have now bounds for these quantities, but we don't know the bias, because we don't know the solution. The point is, can we have a choice of alpha not knowing the smoothness? And that's the goal of oracle type bounds. That's here. So that's a very weak. I'm not a fetishist. So I just take up to logarithmic factors. Everything is nice. So we have seen yesterday there were exponential weighting and so on. The force you get better bounds by other techniques. But Lipsky is simple, universal. I like Lipsky his principle, and Lipsky also. Very much. So what you see here is, we don't know the bias. We have this bound, and this bound was common for both terms on the right hand side, right? We have this bound, and what we want to have, we want to choose alpha in such a way that this bound is minimized up to a log factor. And this is a oracle type inequality for estimation now, right? That's for estimation. But the point is, since the additional term, this trace of the posterior covariance is the same size as the estimation variance. So this is also, if you have a good bound for this quantity, you have a good bound for the contraction rate. That's a major observation, actually. And well, how does Lipsky principle apply? We choose a exponential scale, as you can see, of alphas along some exponential grid. And then what we do, we compare successive solutions, not successive, but at some j, we compare the xj estimate with all previous ones, and we have a threshold which is related to testing, kind of. And that gives you the parameter j bar. That's when you first stop. You start with the smallest value, you just compare with the previous solutions, and you stop whenever you see some signal. That's actually the meaning here. Whenever you see signal, you stop. And what is known is, this is a pointwise posterior contraction rate, and this is of oracle type. Oh, I forgot to mention it, of course. That's an oracle type rate. So, because this will be an oracle type choice for the estimation error, and that's why it will also be an oracle type choice for the reconstruction, for the contraction rate. So this is actually, that's why I like to stress that it's pointwise. That's not uniform in a class, because if you have smoothness classes, you know how to choose depending on smoothness. But here we don't have any smooth. We don't know. We have no idea about the bias, and still we can make something. And that's what I like about the Levski principle very much, because it's very easy to implement, and it's very, how to speak, universal principle. Although you lose kind of a log factor here and everything, that's why statisticians don't like this. But I'm satisfied.
The main drawback is just only for ordered case.
Yeah, it's one-dimensional case, but in our case we have just sequence of alphas. If you have anisotropic spaces, different kind of smoothness, then you need advanced Levski. Still possible, but beyond my knowledge. Okay, that's actually the major achievement in this paper. Just what I want to stress here is the following. Well, what would be a bound for the bias if you have smoothness? What would be a bound for the bias if you have smoothness? And what you see smoothness in these type of problems are Sobolev type, they call it always Sobolev type, although this is a strange notion because T star T is our operator, at least the good friend of T, the self-adjoint operator. And you consider smoothness to be power type, typically in statistics. So phi, the function of phi of T is always T to the mu power type, or exponential. But then it doesn't matter. What you see is if you want to bound the bias here, right? Then you get these estimates which are sharp, and you will see how the smoothness assumption enters. But what is important, and that's why I wrote this slide here, what is important, P is kind of the choice of the smoothness of the prior. So you've chosen a prior with a certain smoothness, P. Here it is. And what you see here is the bias, that's the best possible contraction of the bias, is linear alpha. And that's also lower bounded, that's saturation phenomenon. It cannot be better than alpha. And that's the reason that the posterior contraction rates, even the uniform ones you like, are saturating. So if you have chosen a prior with a certain P, then you capture smoothness of the solution only up to some level. And the level depends on P through this assumption. And then the contraction rate will saturate, it will not be better even if you have more smoothness. And the question in another talk is, is there a way out of the Bayesian setup in order to avoid this remedy? That you get arbitrary contraction rate, arbitrary fast contraction rate, if the solution is arbitrarily smooth. And the answer is yes, the solution is very simple, but has not been observed for some reason. I don't know why. That would be next talk I give in Bayesian. So now the pictures, that's also very strange. PhD students are strange people. Why? So if you look here, you see, oh, the red line, that's the noisy observations. No, that's a true solution. So he chooses a random solution, so randomly constructed on a grid, and then tries to reconstruct in a smooth way. So that's why it looks a little bit strange. But it's PhD students, so here's the a little bit. But as you can see, not here, but on the next slide is, well, these are that's the optimal, the minimizer of this overall functional, but only for reconstruction, not for posterior contraction rates. And you see that if you know the smoothness exactly, you will be close to the minimizer, and if you don't know and apply Levski, you will also be close to the minimizer. And that's at two noise levels, 5 and 10%. So at least for the reconstruction, Levski works very nice, but as we've seen, the problem of posterior contraction can be reduced to the problem of estimation under the strange assumption which I made that you can bound the tail of the sum by the initial segment. And this is kind of artificial, but otherwise it holds in many cases, in all cases studied so far, by the way. And if it doesn't hold, then you just take the bound which you have for the posterior covariance, and maybe it will not be optimal, but it will give some rate. Okay, thank you very much for your attention.
So, questions? Just to clarify, so basically, so Levski himself, so this I know definitely, so they wrote something together. Typically establish the result as a pointwise waterfall, and then derive all the rates and the progress. And somehow the basic notion is something like Oracle inequality or Oracle concentration inequality. Here is everything else and should work as well. So I mean, for me it's a little bit artificial to do rate and pointwise at the same time. So I mean, if you do pointwise Oracle, it's clear, it's established notion. If you do rate on functional classes, it's also established known. But I mean, combination, it's a little bit straight. But I suspect.
But here the point is that you have a class of estimators. You have no freedom to choose your estimators. It's just a parameterized class of estimators, and then it makes sense. It's perfectly conform with the notion of Oracle. So I mean, Oracle is the best choice from the class of estimator. It has nothing to do with functional classes, etc. But so what I'm saying is you can actually, I guess, with the technique you apply, you still derive Oracle inequality, pointwise non-asymptotic Oracle inequality for this Babsky method. Yeah.
And then you can look at asymptotics and show all these results as a corollary, but basically it's a standard way of doing right now. You separate between pointwise Oracle, which is non-asymptotic, and asymptotic contraction rates.
You could do, but the point here is that whenever you impose smoothness, you get exactly the uniform contraction rates which have been observed so far. And you may be better because you have an Oracle. You will not be worse.
No,
but you may be better. No, I understand your point, but if you look at the Knappig's paper, they have their own classes, but there's no reason because they have one set of data, so to speak, so it makes sense to consider pointwise.
Classes only help to control the bias.
Yeah.
Otherwise, it brings nothing. Whether you work with a class or you work with one function, it changes nothing. So basically, when you can control the bias and the procedure is pointwise, you can establish Oracle inequality. I guess maybe Nicholas will show something later on. So he's scared already. We will see.
Okay.
I do hope. Anyway, any further question? If not, Peter once again.